Okay, so today I'm presenting cross-document language modeling. So this is a paper from findings of EMNLP 2021. So it's pretty new paper. Okay, let's start. For the introduction, the majority of the NLP research address a single text, so single document tasks. But there are many important multi-document tasks. For example, cross-document coreference resolution, or classifying relations between the document pairs, or multi-hop question answering. And one example of the multi-document scenario is given by figure 1. So here there are 3 documents, and each document contains a sentence that are actually very similar. So, for example, Harry Scherer is suing blah blah blah. And similarly, in the document 2, Harry Scherer alleges, or document 3 saying it's Scherer was then joined in the lawsuit. So they're all about this suing and lawsuit. And the idea is, given, for example, document 1 and document 2, you can actually recover the sentence, recover the words, the tokens in the document 3. Like, you can recover the joint in the lawsuit, these phrases. So for the modeling, existing language models such as BERT are pre-trained with masked language modeling, self-supervised objective. So this is well known. And for this work, for this CDLM work, this work proposes a simple cross-document language modeling technique to address multi-document language modeling. So the idea is pretty simple. Let me step into the background introduction. So as a background, we need to know something about Longformer. So Longformer is a transformer model with a local attention mechanism that scales linearly with the sequence length. So the ordinary transformer models are in the square time of the input length. So because every token is attending to every other tokens, so it's in n square attention. However, this Longformer model is using a sliding window attention. So this is local attention. Under local attention, each token is only attending its neighboring tokens. And there's a hyperparameter of the window size. So the window size is a constant. So basically the attention is linear to the input size, input length. And Longformer takes the combination of global attention and local attention, like this in figure D. So only some of the constant number of tokens which are manually specified are assigned with global attention to attend to all other tokens. The rest of the tokens by default are local, so they only attend to their neighbors. And as a result, Longformer can take a much longer sequence, such as like 4K or even 16K. So it's longer and longer than typical language models, which only can take 512 tokens for BERT and the Roberta. And however, as a trade-off, Longformer empirically underperforms the ordinary transformer models given the same input length, because if you compare figure A and B, Longformer is ignoring many of the white white attentions in the figure B. So it's not a surprising phenomenon. But anyway, it's because it can take a much longer sequence. So this is the major advantage of Longformer. So as a method, for the method of CDLM, it's actually very simple. So CDLM is built on top of the trained Longformer model. And the idea is to gather all of the relevant documents into a single input sequence. So the input sequence is super long. It's like illustrated in figure 2. So so basically the relevant documents are just concatenated into one single document, one single sequence separated by the special docS and /docS tokens. Just like separating sentences in BERT. And the training is also very similar to the training procedure of BERT. So it's just the task is simply mask the language modeling task, but it's cross document. So you only mask the token in one document, and the model is trying to rely on the other documents to unmask the mask token. And they assign global attention to those cross-document masking tokens, so that the masked token can attend to any other unmasked tokens. This setup is, as you can infer, this setup is very general, and it can be applied to other similar efficient transformers like Big Bird, or any other tokens, transformers. For the actual implementation, they use multi-news dataset as their pre-training corpus data for this specific work for the experiment. The multi-news dataset has 45K of training document clusters, and each cluster contains at least 3 documents. So the distribution is given in table 7. So the cluster basically is, they just concatenate the documents in one cluster into a long sequence and feed to the Longformer model. And for the hyperparameters, they use Hugging Face Longformer base as their model. So they didn't implement new model. And the max, for this work, the max input sequence length is 4K. And for their experimental settings, they build several baselines. The first one is the vanilla Longformer without any pre-training. The next one is local CDLM. So they only apply local attention without any global attention mechanism. And the third one is called random CDLM. So they randomly cluster maybe irrelevant irrelevant document together. The last one is prefix CDLM. So it's global attention for the COS token instead of the masked ones, resembling the Big Bird model. So COS token is basically the first token of the first special token of the input sequence, which is usually used as the document or sequence representation. Okay, and for the evaluation, they use both intrinsic and extrinsic evaluation. For the intrinsic evaluation, they use the perplexity as a metric. For extrinsic evaluation, they have 4 tasks: event and entity cross-document coreference resolution. The second one is paper citation recommendation. Third one is document plagiarism detection. The last one is multi-hop question answering. And let me go over them one by one. So for this paper, most of the parts are their experiments and verification of how useful their CDLM is. So perplexity is basically the exponentiation of the loss. So the lower, the better. And oops. So the result is given in table 1. So apparently their best configuration, CDLM performs the best. So the test perplexity is the lowest one. And for the ablation, they obtain the following conclusions. So the pre-training overrated document helps. This is actually by comparing random CDLM and CDLM. And by comparing the prefix CDLM and CDLM, they find their difference is small because basically it's more like a design decision. So prefix CDLM also use global attention, but on CLS tokens. And lastly, they found global attention helps because when they compare local CDLM versus the CDLM, the difference is pretty large. Okay, for the next task, the first extrinsic evaluation, they work on cross-document coreference resolution. So for the data set, they use ECB plus corpus. So this is about within and cross-document coreference for entities and events. Their model is still apparently using Longformer with CDLM, but with some modification. So this figure shows their model, which is a pairwise, which serves as a pairwise scorer. So for the input, they add special mention tokens to the mention of like entities or events, and they let the yellow tokens to be global and the blue tokens to be local. And given the output of CDLM Longformer model, they perform this kind of summation on the mention token representations, and they concatenate the COS and the summation of mention tokens and the element-wise product of mention representations. They concatenate these 4 parts together as a single vector, and they use this vector as the score. Given this score, they use agglomerative clustering to form the coreference clusters. So this score, this M vector, is the representation of this similarity of the the mention pairs. So for the results, they did a lot of experiment, and again, apparently their CDLM performs the best. Here, it's the higher the better, and it's not very surprising. And they also mentioned that some of the works, some of the baselines are actually using like better settings, but still their CDLM largely outperform the previous baseline. So it's an amazing result. For the ablation, so they also showed ablation studies for this coreference resolution task, and they showed that each of their mechanism, like global attention and relevant document clustering, all this helps. And one thing to note is sentences only CDLM means they only feed the sentences that having mentions, and without feeding other contexts. So this comparison shows that the entire feeding the entire document also helps. But previously, because previous models are not able to take very long sequences, so they could not take the entire document as the context, which is actually helpful. Okay, let's step into the next experiment. So for the document matching, there are a few benchmarks. The first one is citation recommendation. For citation recommendation, they have 3 data sets. The first one is ACL Anthology Network, which contains purely NLP papers. And the second one is called the Semantic Scholar Open Corpus. So it contains computer science and neuroscience papers. The third one is Stork. So this is a pretty famous data set released by Allen AI. So it's a huge corpus, including broad science, including like many subjects of science papers. For the plagiarism detection task, they use PAN dataset. So it's about, it contains web documents with some plagiarism phenomena. For the training of this document matching task, they assign global attention at the CLS token. And as I said before, CLS token is placed at the beginning of the input sequence. So the results is given by table 4. So not surprisingly, CDLM outperforms all other baselines, except for PAN, the plagiarism detection task. That's because they found that PAN does not seem to require detailed cross-document attention at all. So the BERT HAN, BERT Hierarchical Attention Network, actually performs the best because it does not use the cross-document information. So for the next task, it's called the multi-hop question answering. Their benchmark is Hotpot QA distractor dataset. So it contains a question and 10 paragraphs, 2 of which are useful, like containing actual evidence, and 8 of them are distractors. So they are garbage for this question. The the task is the first one is to extract the correct answer spans from the given paragraphs. And the second task is to detecting the supporting facts, so detecting the evidence sentences. For the algorithm to perform this task, they basically employed the Longformer setup. So they concatenate the question and all 10 paragraphs into one giant sequence, separated by document token. And the sentences, because they also perform sentence level tagging, so their sentences are separated by special tokens. And they use multitask learning with classification heads specializing on relevant paragraph prediction, evidence sentence identification, extracting answer spans, and inferring the question types. So basically, they use multitask learning to perform all of the relevant tasks together. So the result is given by figure 5. They said CDLM outperforms all other baseline models except Big Bird, because Big Bird was pre-trained on much larger data than Longformer and CDLM. So CDLM, remember, it's based on the Longformer base, so it's not theoretically the best model, the strongest model. Yep. Then finally, they perform so after the experiments, they finally perform analysis. So they study the attention, their attentions in the CDLM Longformer model. So for this setup, the benchmark is the randomly sampled 1,000 positive and 1,000 negative coreference pair examples from the ECB cross-document coreference resolution benchmark for both events and entities. So they use the benchmark they used previously. And the examples looks like this. So for example, the document 1 says President Obama will name Dr. blah, blah, blah. And in document 2 says Obama nominates new Surgeon General. So here, the phrase name and nominates are coreference, and they are already like annotated. So for the attention analysis, the idea is to look at how strongly the phrase name and the phrase nominates attend to each other. So the specific method is first identifying the source and target spans. Basically, it's just name as the source, target as the nominates as the target span. And then they take the attention weights from the last layer of the model. So the last layer of the Longformer, and compare the percentile rank of the normalized score of the source target pairs versus the source other pairs. So just like I said, they just compare the how strongly the source span, target span attend to each other, comparing to the source or target span attending to any other tokens. So obviously, high value of this score of source and the target span attention score implies high percentile rank. And the the percentile rank of 50% correspond to a random ranking, as you can infer. So the equation here is basically introducing how they compute the attention score. So it's just pretty straightforward to understand. And note that they consider like bidirectional attention. So they add the bidirectional attention together. So they add the attention from nominate to name and name to nominate together as one term. So here's the result. It's also pretty straightforward to understand. So first, let's look at the positive versus negative MPR, so mean percentile rank. So apparently, positive for those positive examples, the MPR are just significantly higher than the negative examples MPR, because like the model learns to attend to the relevant like coreference phrases. And then if we compare the global CDLM versus the local CDLM, global CDLM apparently has a higher, much higher MPR than local one, which is also repetitively verified by the previous experiments. Okay, this concludes their paper. And for this paper, my comment is that the CDLM approach is shown to be very effective using multiple experiments. And the approach is simple to implement and very widely applicable to many different cross-document scenarios, like different models or tasks. For example, in my case, I use another model called LED, and I work on different tasks, which was like really work annotation tasks, and I can still use this idea to pre-train my language models. However, as a slight disadvantage or limitation of this work, they only work on the encoder model. So Longformer only contains a transformer encoder, but the encoder decoder version is not provided. But it is actually pretty easy to implement when I was using LED, so Longformer encoder decoder model, we didn't have much difficulty to implement this same CDLM mechanism. So that's it for my presentation. Do you have any comment or any question?